Well, yeah, it's a pleasure to have our first speaker of the fourth semester, his seminar today. And Fuqiang is no stranger to all of us. And he got his PhD from Columbia, I think, in 1996. And afterwards, he came to Berkeley as a postdoc from 96 to 2000. And then afterwards, 2000, he became assistant professor at Purdue University, and then he became tenured in 2009, and now from 2009 he became 2009 he became the full professor at Purdue University. So today he is going to talk about a very exciting new topic. Is Isobar result from star in search for the chiral magnetic effect. And I think many of us already heard the star seminar last Tuesday, and many of us have a lot of questions today. Fuqiang is here to answer some of those questions. Fuqiang, take away.
Okay. Thank you, Xinyan, for the introduction. It's so nice to be here, even though it's virtual. I saw many people. I spent time in Berkeley for several years. Saw Peter Jacobs on the screen. New hi Peter. So it's a great pleasure to give this seminar, and I want to thank Xinyan for asking me to talk about the freshly released Isobar data by STAR. It was released 2 days ago on Tuesday, and Xinyan asked me to kind of present the results and my take on them, my perspective on the results. So first of all, a disclaimer. This is not a talk on behalf of the STAR collaboration. This is my understanding of the STAR Isobar results and my take on them. That's what Xinyan asked me to do. So the title is Isobar results from STAR in searching for the chiral magnetic effect. So I'm going to, I will not talk about Isobar's data only. I will kind of give a brief history of the chiral magnetic effect search in heavy ion collisions over the past decade, more than a decade, actually. And then I will discuss to some degree of not much details, but I will discuss about the latest experimental knowledge before Isobar. And then I will report on the Isobar data, the results from the Isobar blind analysis by STAR. And I will present my view on the next steps that we need to do, and a brief summary at the end. So this is meant to be a very informal seminar, and I want to ask if you have questions, interrupt me at any time, because if you have questions and we can discuss. And I don't know about the time, but I try to finish within 1 hour. So first of all, and about CME, I don't have to say much about it. Most of us are aware of the importance of the physics of the chiral magnetic effect. So this is related to the so-called theta vacuum term in the QCD Lagrangian, the topological gluon field, and so the theta term, and the theta value is 0 in present universe, but the idea is that it may not be 0 at the beginning of the universe, and therefore you should have vacuum states with different values of the topological charge, which is really the dot product of the color electric field and the color magnetic field. And you can have, because the temperature was high, at the early universe, you can have, probably appreciable probability of transition between different vacuum states through, instant and spheroron mechanisms. The interactions of quarks with this topological field will produce the chiral anomaly, basically, that you're going to get different numbers of left-handed quarks and right-handed quarks. And if you have a domain of unbalanced chirality, and if you put that domain into a strong magnetic field, then the quarks will separate according to their charge, because their magnetic moments are proportional to their charge. And therefore, it will have consequence in the final state, basically charge suppression. And we think that we do have a very strong magnetic field in heavy ion collisions. Of course, it's a big question, but heavy ion collisions provide a unique opportunity to us to study this physics. Moreover, as you can see, I wrote on the slide that this vacuum term explicitly breaks CP. So it could offer an explanation for the antimatter asymmetry of our universe, because we know the physics behind it is the CP violation, but the magnitudes of CP violations in weak interactions just not enough to explain the magnitude of our matter-antimatter asymmetry in the universe. So the physics is clearly very important, and therefore, a lot of us in this field have spent a lot of time looking for experimental evidence of the chiral magnetic effect. So what we're looking for is really a charge suppression along the direction of magnetic field, which is on average perpendicular to the reaction plane. We use the common gamma variable. This is proposed by Sige Voloshin in 2004. So it's the variable is rather straightforward. It's a mean cosine of the azimuth angles of two particles relative to the reaction plane. And you can plug in the angles of this configuration, and you know that the gamma value for unlike sign, which are back-to-back, will be +1, and the like sign pairs will be -1. We have a lot of particles, so there is, of course, dilution effect. You take, this quantity divided by the total number of pairs. So the magnitudes that we measure are small, and this depends on the size of the event and the initial signal strength. Also, meanwhile, there is a charge-independent background, like global momentum conservation. So people usually use the difference between the opposite sign pairs and the same sign pairs. And that difference should be positive for the CME. So this is the main observable that people use. Large delta gamma measurements. We've measured large delta gamma everywhere. The initial measurements were from STAR in 2009. It's gold-gold collision, copper-copper collisions. This plot is from a publication in 2013, but the first measurement was from 2009. There is a rather large separation between, or different measurements of OS pair and SS pair gamma quantity, and the difference between them, which is a delta gamma, is rather large. The magnitude is on the order of 10 to the -4, but that's considered to be quite a large, because this is two-particle correlation measurement. 10 to the minus 4 means you should take a square root of that. And that means 1% of the particles are affected by the CME, if this is the CME signal. So that's quite large. The middle plot is from Ellis measurement back in, I don't know why, back in 2013. And also star measurements from 2014 in beam energy scan at different energies. And we see a large delta gamma results at different energies. And it dies off when you go to lower energy, like 7.7 GeV. So large delta gamma measurements. But we also have measured the large delta gamma in small systems. This is the left plot is CMS measurement in P-lead compare with lead-lead. And the right plot is star measurement in D-gold, P-gold collisions compared with gold-gold collisions. And as you can see, the small systems follow, if you can kind of look at the plots, they are trends, and the small system seems to follow the trends of the heavy system, heavy ion collisions. Now, this doesn't really mean that the small systems and larger systems have the same physics. I'm sure that the correlation, the physics behind the correlations are different, or at least not identical. But the large, because we do not expect CME to be observable in small systems, and this is because the magnetic field direction and the harmonic direction that we measure in experiments are random with respect to each other. So you should not observe any CME signal in small systems. The fact that the delta gamma in small systems are large already give you some, so we have to be very careful about the interpretation of the larger system. This does not mean that the larger system must be all background, but in order to conclude from the larger system results that there is CME, we have to do a lot more work to convince ourselves that that's not a background. So what is the background in delta gamma? It's really due to the simplest example would be resonance decays, producing angular correlations between the two daughter particles. And because resonances have flow, elliptic flow, now these angular correlations become reaction plane dependent. So it's a coupling between the decay angular correlations and V2 of the resonances. This is a background because this decay pair from rho, for instance, and a back-to-back CME pair in red, they give you the identical delta gamma, the mean cosine, if you plug in the angles. And this was realized early on, right from the beginning. And many people. It's really that there's no question about the existence of such a background. The question is really how big that is, and whether that can explain the measurement of delta gamma. So this background is proportional to V2, is proportional to the clusters, the V2 of clusters, but we know that the V2 of the clusters is proportional to the final state particle V2. They do not have to be identical, but they have to be proportional. There's no reason that they're not proportional to each other. It's inversely proportional to multiplicity, and that's simply because this is a pair-wise quantity. So suddenly it's proportional to the number of rows, and you divide by the total number of pairs, which is multiplicity squared. And then if the row multiplicity is proportional to the pion multiplicity, then you get automatically 1 over n. So the background behaves like V2 over n. Now, many model studies and theoretical studies show or demonstrated or simulations indicate that the backgrounds are really large. And here I have two calculations. One is from Scott and Soren. They used blast wave calculation with charge balance and using parameters which describe the overall bulk properties of data. They could basically explain entirely the delta gamma measurements by this background, the charge conservation, local charge conservation background. The right plots are from a paper published by Volker, Jimfen, Adam, back in, I think the first paper was 2010. This is probably the second paper. So they decompose, so basically they told us that, there is large background and it has in-plane, out-of-plane. So you have two terms, cosine, cosine, sine, sine. And they are quite different between opposite sign and the same sign. So this is a large piece of background. And the question is really that how much is still left for the CME signal from all the delta gamma measurements. And this is really a tough question to answer because you cannot, although that model studies are very important, but you cannot rely on them. You have to measure them. And then this becomes difficult. Yeah, I forgot to mention that you can do a back of envelope calculation and you see that this background is on the order of 10 to the minus 4. Basically, I take number of rows to be 20, number of pions to be 100. That's about right. This angular correlation of row decay with typical momentum is 2/3. A typical flow is 10%. That gets you to 10 to the minus 4. And that's what we measure in heavy ion collisions, in medium central collisions. Later experimental results confirm that background is really large. One type of measurements is using the event shift engineering technique. The left top plot is actually from an early STAR study with event by event V2 measurement or event by event shape measurement. So you look at a quantity that is very similar to delta gamma as a function of the event shape and event by event, and you see a nice linear relationship. Now this the horizontal axis is event shape quantity, we call it V2 observed, and this is dominated by statistical fluctuation. So basically we're using statistical fluctuation to get a gauge on the background. If you do a fit and the intercept, which is at 0 V2 observed, that would be more sensitive to the CME, and we get 0, so consistent with 0. LHC experiments can do better analysis of this event shape engineering technique because they have a wide pseudo-rapidity coverage. So they can really select events with using the Q vector at the some phase space and look at V2 of your interest, of your particles of interest at the middle rapidity. And they plot delta gamma as a function of V2, the ELLIS and the CMS. The details of the analysis are different, different ways to take care of the magnetic field variation within a centrality beam, depending on the Q vector. But the overall conclusion was that the intercept from this linear projection is consistent with 0, and they extracted upper limits on CME 26% from Alice and rather stringent upper limit from CMS. But again, the details are different. So these numbers, you should not take very, very strictly. But the point is that the CME upper limit is on the order of 20% at the LHC. The right plot shows now the invariant mass dependence of this delta gamma. And you see on the top plot is the resonance spectra, and the bottom delta gamma, and you see similar peaks. So really that the delta gamma is dominated by those correlated clusters. I said not just resonance. You can have continuum of neutral clusters. So this means that the background is really large. Now coming to the most recent measurement from STAR, and this was submitted for publication a few months ago. The idea is really simple, straightforward, and neat. And this is the following: that we make delta gamma measurement. We don't know how much background there is inside the delta gamma. But we can make two delta gamma measurements in the same event because we have two different planes, harmonic planes. One is the participant plane, which can be reconstructed in STAR by the TPC particles, and that corresponds to the participant plane or the V2 harmonic plane. The other plane is the spectator plane, or if you will, the reaction plane. And they're different because of event-by-event fluctuations due to finite size of the nucleus. Since these two planes are different, now you can have two delta gamma measurements. These two delta gamma measurements have different contributions of the CME signal and the flow background, because the flow background is with respect to PP, and the magnetic field is with respect to the spectator plane. So you have two measurements and two unknowns. So you could just simply work out the two unknowns. So now you can have separate measurements of the background and the signal. So the right plot is the FCME, the CME fraction measurements in gold-to-gold collisions by STAR. Two sets of data points. The blue points are peripheral collisions. And so the FCME is the fraction of CME contribution in the inclusive delta gamma measurement. The peripheral collisions are consistent with 0, although the error bars are large. The medium central collisions, the error bars are also large, but there is an indication, a hint at least, of a positive CME signal. I should say that these 4 data points are not independent. These are 4 different ways or methods to analyze the same data. The 2 points on the right are using the sub-event method, meaning that you divide the TPC into 2 sub-events. So you have some eta gap in between. You measure event plane from one sub-event and your particles of interest to measure the delta gamma from another sub-event. So you reduce the non-flow effect. So the non-flow contributions to the points on the right, the 2 points, is smaller than the contributions to the left 2 points, which are the 4-event method.
Excuse me, can I ask a question? Sorry.
Yes, Cafe, yes.
Yeah, the fraction of a CME, how is that defined? How does one know which one is CME, which one is background?
Yeah, so here we do 2 measurements of, so we have 2 delta gammas with respect to 2 planes. And in each of these delta gammas, you have CME contribution and the background contribution. So you have 2 equations, and you can just solve for CME and the background. I did not have the algebra written here, but in other words.
But one would know, but wouldn't one know that if I have a CME, the delta gamma has to be this, and if it's background, the delta gamma has to be something else? Is that clear? How?
Well, so let me explain a little bit more here.
Okay.
You have the CME signal along the magnetic field, and you have the background along the flow plane.
But how does one define the CME signal?
Oh, it's not defined. We just make a measurement of the delta gamma, and it's a single measurement with respect to a single plane.
Mm-hmm.
So, for example, you take the reaction plane, right? You do a delta gamma measurement.
Mm-hmm.
Now you take the reaction, the participant plane, and you do another delta gamma measurement.
What is a participant?
It's the V2 direction. It's the V2 plane. Okay. So you have I have a cartoon here. So you have this overlap, and so this is your impact. The horizontal direction is your impact parameter direction.
Mm-hmm.
Your overlap has fluctuations. So sometimes you can get an elliptical shape.
Right.
The short axis along the arrow of PP, psi PP.
Okay.
This is the flow plane. We call it flow harmonic plane. The second order harmonic plane.
Mm-hmm.
And along the second order harmonic plane, psi PP, you have the maximum background contribution.
Mm-hmm.
Because that's V2. And the magnetic field is perpendicular to your reaction plane.
Mm-hmm.
So the CME is along the reaction plane. Therefore, in your measurement along PP, it's a projection from the magnetic field onto PP.
Mm-hmm.
So this angle matters here. Now, we don't know the magnetic field direction,
mm-hmm.
But on average, it's perpendicular to the reaction plane. And similarly, you make a delta gamma measurement with respect to the reaction plane.
Mm-hmm.
The CME is entirely in the reaction plane measurement.
Mm-hmm.
You can consider this to be a magnetic field direction.
Mm-hmm.
And then the flow, which is along the PP direction,
mm-hmm.
Now it's a projection onto reaction plane.
Mm-hmm. Okay.
So now the flow would be smaller. The flow background will be smaller along the reaction plane direction.
Mm-hmm.
So basically you have two equations and two unknowns. And you can work out the delta gamma CME and delta gamma background.
So you define the CME to be somehow, is it along the magnetic field or perpendicular to the magnetic field?
It's along the magnetic field.
Along the magnetic field, right?
Yeah,
right.
perpendicular to the reaction plane.
Right. Okay.
Yeah.
Thank you.
Yeah. I have equations on one of the later slides, but not much detail, just to have the results. So the upshot is that the peripheral collisions are consistent with 0, and medium central collisions indicates a signal which, with a significance of 1 to 3 sigma. And very important, I want to point out that there is still possible remaining non-flow effects in those measurements. And we said that in our, in the STAR paper, we did not do a simulation or study, but we basically discussed about it. And I will discuss about the non-flow or estimate of non-flow effects in this talk, later in this talk. Yeah. So this is I would say the latest status of CME in experiments. Now coming to isobar collisions, so we now know that the background is large, and the idea of isobar collision is very simple. we have two isobar nuclei with the same number of nucleons. The mass numbers are the same. Therefore, we expect the QCD background to be same. And they have these two nuclei contain the different number of protons, and therefore the magnetic field will be different by 10% also, and therefore the CME signal will be different by 10% also. And since we measure delta gamma, the delta gamma will be different by square of that, so it's 20%. Model simulations indicates that the effect is about 15%. We expect 15% more delta gamma CME signal in ruthenium collisions than in zirconium collisions. Only 15%, not 20%, is because the protons in the zirconium, even though 4 protons fewer, the protons are more closer to the center. So they make a slightly bigger contribution to magnetic field, relatively speaking. So it's not 20%, but 15%. But that's detail. This is a famous plot back from 2016 by Deng and Guang, a projection of significance given statistics of isobar collisions. So their estimate in their paper, they used 400 million events, and they estimate the significance of a measurement as a function of the background level. So if the background is 2/3 of the delta gamma measurement, then with these statistics, we should get 5 sigma effect. We actually have more, factor of 5 more data taken in the isobar round, 2 billion events each. This would mean that the significance will be factor of square root 5 larger. So with 2/3 background, 1/3 signal, we expect 11 sigma effect. Now, this is, of course, overly optimistic. We now know that gold data indicate maybe 10% or even smaller FE fraction, CME fraction. If the signal is only 10%, then this would mean about 3.3 sigma. So if the signal is 10%, we expect about 3 sigma effect in the isobar data. Now, this is from their paper, and you can actually do a very simple back of envelope estimate of the error bars, of the significance. The error on the delta gamma measurement would be, a single pair cosine would be, a sigma of, it's a uniform distribution between -1 and 1, so therefore 2 divided by square root 12, divided by the number of pairs square root. This, we are taking delta gamma, so it's square root 2 bigger here, and then divided by square root number of events. Now we focus on medium central collisions, so 0.7 billion each. We have event dependent resolution of about half, so the error bars will be bigger by a factor of 2. We get about 0.8 times 10 to the -6 statistical error for delta gamma. You will see that the delta gamma from isobar collisions is about 3 times 10 to the -4. So that's about 0.3%. Now we do comparison between 2 isobars. We take a ratio, so it's additional square root 2. So the statistical precision will be 0.4%. And actually you will see that we do achieve 0.4% from the isobar data. So what we're expecting is really this, right? That 15% magnetic field difference, 10% signal. So we're looking at 1.5% difference. So it's about 3-4 sigma effect. So consistent. Very recently, we realized, and I still, kind of blame myself that, I did not realize this early on, because this is rather simple. So we had several months ago, we had a large statistics AVFD simulation, and we were looking at AVFD simulation results of goal-to-goal collisions and isobar collisions, and we couldn't understand the results. But only shortly after, we realized suddenly that the signal-to-noise ratio in isobar collisions cannot be 10%, cannot be as large as goal-to-goal collisions, or at least that's my naive kind of expectation now. This is because the isobar collisions have fewer particles. Therefore, since the background is inversely proportional to multiplicity, you expect the background to be higher by a factor of 2 in isobar than in goal-to-goal. The magnetic field in isobar is smaller by factor of a to the 1/3, so 2 to 1/3. So the square of that would be factor of 1.5 smaller. So just from that simple argument, you expect a factor of 3 reduction in the signal-to-noise ratio from goal-to-goal to isobar collisions. Now, this is just very simple estimate. The biggest uncertainty, there's no uncertainty here, I would say, but the biggest uncertainty is in the signal. It could be possible that the signal, the initial CME signal in isobar is bigger than goal-to-goal. Then, of course, your signal will be bigger in isobar. But from this kind of mundane physics expectation, if the signal is factor of 3 smaller, then we are really talking about 1 to 2 sigma effect from the 2 billion isobar collision for each system. Or in other words, we're talking about a fact like that. It's really 0.5% plus or minus 0.5%. With that, well, a couple of slides, and then I'll go to isobar data. Hopefully, I will not run over time too much. The elliptic. So all we have assumed so far is that the backgrounds will be the same between the isobars. That's not true. The elliptic flows can be different and are different. If you have different deformities, then the elliptic flows will be different, but they only affect the central collisions. The medium central collisions are not affected much. We had a nuclear structure calculation by the density functional theory, DFT calculations. And just because the number of protons and number of neutrons are different between the 2 nuclei, even though the total number of nucleons are the same, the nuclear structures are different. And that difference gives you a difference in the eccentricity on the order of 2 to 3% here. So this is a prediction, but that is okay. Even though you have a background difference, you can divide the V2 out, right? Because you measured the V2, and this is just a simple formula from one of the previous slide with the 2 particle cluster or the low resonance. So we can take delta gamma over V2, and here this is the multiplicity dilution, so we should multiply the multiplicity before delta gamma. So this would be the variable that we would look at. Now, we can, of course, divide out the V2, but if the backgrounds are different, then since our V2 measurements are not purely flow, it has non-flow contributions. So there will be complications due to non-flow that I will talk about. To conclude about my understanding shortly before the isobar data, from goal-to-goal collision to isobar collisions, the reason we want to do that is because we expect increase. We expect a 15% difference in signal, but only 2 to 3% difference in background. So we gain a factor of 6 in the signal over background ratio from gold-to-gold collision to isobar collision difference. But if the signal is really only 1/3 of the signal in gold-to-gold, then we're talking about only factor of 2 gain in the signal to noise ratio. And actually what's more relevant is the significance, signal over square root background. Then actually, if you have background of 2.5%, then in terms of significance, you do not gain from gold-to-gold to isobar. In other words, with the same number of events, you should get the same significance from gold-to-gold collisions alone or from isobar collision difference. And of course, if the signal is bigger in isobar than gold-to-gold, then of course, isobar, the power of isobar data will be stronger. And I should say that there's a big uncertainties there, theoretically. So coming to isobar data now, this was released 2 days ago, and I have links of the talks of the Brookhaven seminar at YouTube, and the paper was submitted and it's on the archive. It's a tremendous effort of STAR. Many people are involved. I would say the entire collaboration was involved. It's an effort of 3 years from taking data or preparation for data taking to the release of the data, release of the final results, not the final results, but the isobar blind analysis results. These are the multiplicity and elliptic flow from isobars. So first of all, multiplicity, that's the first thing that you want to look at. So this plot is the ratio of ruthenium over zirconium multiplicity distribution. And the data are the gray points. The red crosses are the global model calculation simulation using nuclear structure densities from DFT calculations. And as you can see, the agreement is rather good. It's not perfect and there's room for improvement, but it's really, I'm pleased that actually it's such a good description of data. And it's a real prediction. This is I should have said it's in the PRC paper, but it's also in the PIL paper, but not plotted. So this is the prediction of the multiplicity distribution in red. And the reason for this multiplicity, a bigger multiplicity, a larger multiplicity in ruthenium collisions than zirconium, and that's why the ratio is bigger than 1 on the tail, is really because the size of the ruthenium nucleus is a little bit smaller than the zirconium nucleus. Because the zirconium nucleus has more neutrons, and neutrons tend to be fatter, so it has a thicker neutron skin, and therefore the overall nuclear size of zirconium is bigger. And because of that, in the collision, the energy density in zirconium will be smaller, slightly smaller, and therefore the multiplicity produced is slightly smaller. Elliptic flow, this is the isobar data, again, ratio. So it's a V2 ratio of ruthenium over zirconium. And as you can see, you have this characteristic, well, not characteristic, but this shape, strange shape. And this is actually predicted 2 years ago by the nuclear structure calculation. This is the eccentricity ratio, 2 to 3%, and that's what we see. And the central collision here is not predicted because this is a spherical nuclear. So the nucleus, the nuclei are assumed to be spherical. This we think is due to different deformation. So a larger deformation of the ruthenium nucleus than the zirconium nucleus. So therefore, the deformation has the largest effect in central collisions. Quite neat is here that this is not very important, but I can help to mention. The ZDC, the V2 measurement with respect to ZDC plane or spectator plane, the ratio is actually rather big, actually going up beyond 10%. This is data. And this is actually also predicted, at least semi-quantitatively. And this is this one, 10%. And the reason is the following. The nuclear structure results from DFT calculation is such that the spectator plane angle in ruthenium is in ruthenium collisions is closer to the reaction is closer to the participant plane angle than that in zirconium collisions. That is, this is a mouthful. That is to say that the correlation between these two harmonic planes is stronger in ruthenium than in zirconium. And therefore, because flow is along the participant plane, flow with respect to ZDC or spectator plane is just a projection of the real flow onto the ZDC plane. Since the correlation is stronger, the projection would be bigger in ruthenium collision. So you start off with a 2 to 3% bigger V2 in ruthenium already, and then the projection is stronger, is bigger. So you get a 10% difference. And that's also kind of predicted. Now come to the CME variables, delta gamma over V2. That's what we defined before Isobar blind analysis. We have 4 groups who analyze this quantity. And as you can see, the consistencies are very good. Of course, they are same data. So the statistical error bars are correlated. The data points are not identical because different groups have different, slightly different cuts and different methods. And we actually verified that the difference in the data points are consistent with those differences due to the cuts and the event selections. And this is again the ratio of this quantity in ruthenium over zirconium. The ratio is below 1. And the naive expectation was 1. It's below 1, and there's a good reason for that. This is due to multiplicity difference. This is the multiplicity difference here. So this is the average multiplicity in these two systems, and this is the ratio at the bottom. Ruthenium over zirconium. You have more 4.4% more particles in ruthenium than the zirconium. And we know that all along that these will be diluted by multiplicity. So simply because ruthenium has larger N, you will get a smaller delta gamma for the background. So I basically flip the lower plot of this ratio here, and you see that this is the inverse multiplicity ratio, and this is the delta gamma over V2 ratio. Now this shape, this wiggle is not something that is due to real physics, but it's due to a slight mismatch in the centrality definition. It's not precisely 40%, 50%. There is some difference between the two systems. But the overall trend must be physics. Okay. But we've defined this variable before the Isobar blind analysis, so we had to stick with it. The multiplicity scaled variable would be better. This is the delta gamma measurement, the delta gamma over V2 on the from one of the groups. So one of the data sets on the previous slide, and the kappa measurement. The kappa is delta gamma over V2 and divided more with an additional division by delta delta. And delta delta, I don't have, delta delta is the mean cosine alpha minus beta. So it's the mean cosine delta phi between the two particles. And this is predominantly background. There is some CME contribution to delta delta, but I think that can be neglected. And this is the kappa. Now, the multiplicity dilution effect is canceled in the kappa variable because both delta gamma and delta delta will have 1 over n dilution. So this quantity, the baseline, the naive baseline would be unity. And we found that this is actually below 1. And I have a reason for that. I have an explanation in my view. So all of these are naively unexpected. And the main reason that all those ratios are below 1 is because of the multiplicity difference, except the kappa. So the multiplicity difference of, in delta gamma over V2 is just the inverse multiplicity difference. We have.
Will you tell us later why you think what the reason for the difference in delta kappa is? Or what your own view on this is?
Yeah, I will get to that.
Okay, I'll wait.
But Volker, it's non-flow. It's a non-flow difference.
Non-flow. All right.
Yeah.
That seems to be the famous carpet where everything else goes under, right?
Yes, and it's a nasty thing to
okay, I'll wait for the explanation.
Yeah.
Okay, go ahead.
Yeah. So we look at the invariant mass distribution of the delta gamma. We make measurements of the little r, which is basically the relative pair multiplicity difference, and this is this quantity pretty much. We take, so this is the ratio of this quantity, strictly speaking, this quantity, and this is the delta gamma in the two systems, and this is the ratio. I'm sorry, this is the difference of the delta gamma in ruthenium minus zirconium with a factor to take care of the difference in the background. And here, this A prime is the V2 ratio because that's one part of the background difference. And the initial idea was to have this little r in this A prime. So we should put this little r here, but we didn't somehow. Well, it's in the bookkeeping. It's an overlook in the bookkeeping. We did not write it in the analysis note. So we have to stick with the brand analysis procedure. But the difference of this is supposed to be the CME signal as a function of invariant mass. Okay, right now it's consistent with 0. We also do CME fraction measurements, the one that I discussed in terms of goal-to-goal collisions. By the way, carefully, these are the formulas of the results. This is the CME fraction. It's due to, so this is the CME contribution in the delta gamma measurement with respect to the TPC particles. And this is just a double ratio -1 divided by a factor. These are these measurements, 4 events and the sub-events, and all of them are consistent with 0 within 1 to 2 sigma. We can also get a constraint between the FCME in ruthenium and FCME in zirconium by taking the because we know the relative background between these two systems to be proportional to V2 and inversely proportional to multiplicity. At least that's the first order expectation. We can do that, and you can get an equation like this to connect these two FCMEs. So this will be the diagonal strip, the dark diagonal strip here. Again, this in here, this A prime is the V2 ratio, and we should really have included the multiplicity ratio as well. So with the A prime only V2 ratio, the dark strip is here. And the idea is actually, with the individual FCME measurement, this box, and this constraint, this would be the overlap region. So this would be the allowed CME region. From theory, from magnetic field expectation, we know that the signal would be between these two blue lines, right? Because you expect a difference between the signals of 15%. So this is 15% plus minus 2 sigma, sigma assumed to be 0.05. So that's kind of a theoretical uncertainty for the magnetic field. And there's no overlap at all. And this is because we did not include the inverse multiplicity ratio in this little A prime. If we do, then this double ratio will be only 1% away from 0 with relatively big error bar. By the way, this is not 0.004 because this is for pions. So it's identified pions. So the statistical error is bigger. With that, now this equation is actually the red lines here. So this would be allowed region of CME. And now there is overlap between the red and the blue. And I know that you can't really, it's hard to look at that. So there is an allowed region of CME, FCME. This region right now includes the 0 here. So 0 is not excluded. All right, and these are the money plots of the Isobar paper. So we make the ratios of delta gamma over V2 between the two systems. We make ratios of kappa and a similar quantity, K, between the two systems. And we also have the third harmonic quantities, the counterparts. They have larger error bars because of V3. This is the blind analysis results. And we wanted to put in, because of the multiplicity difference, the baseline, the naive baseline of unity is clearly not correct. The naive baseline for the delta gamma over V2 would be the ratio of the inverse multiplicity, this line. And I also have a line going through this little r ratio, because little r ratio is also a baseline expectation, because this little r measures the pair difference, which is kind of more relevant than the multiplicity difference. But I should mention that, I should emphasize that this little r right now is measurement for pions, not charged hadrons. Okay? But if I take the inverse multiplicity ratio as the baseline, then the delta gamma over V2 is above that baseline. Or in other words, the delta gamma over V2 times multiplicity would be above unity within 1 to 3 sigma, depending on which data points you look at. Not big significance, but it's above unity. The kappa, the kappa, the naive expectation is 1, and there's no multiplicity scaling here, so it's below 1. And now coming to the reason, my explanation for kappa being smaller than 1. Kappa is really the delta. Kappa here is delta gamma over V2 times n over n delta delta. I have the n's in both numerator and denominator. And this is the quantity that we looked at. the delta is really the two-particle angular correlation, and that's just some correlation, some correlation quantity, and I call it non-flow, but it's probably not precise terminology. It's basically a delta phi correlation, and this delta phi correlation is different between the two systems. In fact, we measure the delta here, right, in two systems, and we take the ratio of delta between the two systems, delta, and the ratio is below 1 by 1.5%. But the real quantity is so delta is also multiplicity diluted. The real quantity would be multiplicity times delta. And therefore, and this is, I call it the non-flow, angular non-flow. And the difference between ruthenium and the zirconium is about 3%, because the multiplicity difference is 4.4%, minus this 1.5%. So it's about 3% difference. So this means that the angular correlation non-flow in ruthenium is bigger by 3%. So in other words, if the naive expectation for N delta gamma over V2 is unity, then the naive expectation for kappa baseline should be 97%. So it's somewhere here, okay? So we shouldn't take the unity as the baseline for kappa. So with that kind of a positive tone, now come in really the nasty thing, and I will take another 10 minutes if I can. The remaining non-flow effects, and I'm now back to the FCME measurement in a single system, goal-to-goal collision. This is the FCME formula, and this is the double ratio. This is the relevant quantity. And we did a non-flow study in this preprint several months ago. So this double ratio is really the delta gamma over V2 with respect to ZDC plane, spectator plane, divided by that with respect to participant plane. And we measure things in terms of the three-particle correlator for the TPC correlations, at least here. And I've just write it here for the ZDC, but it's not really C3. Now, the non-flow is in here, is in the TPC measurements. There is no non-flow in the ZDC measurements because those are spectator neutrons. They do not participate in the collisions. So there's no correlation. There's no non-flow correlation. I should note that the background we have talked so far due to resonance decay and the flow, this is the main background for delta gamma. So in a sense, this is a non-flow background due to decay coupled with flow. And we always call that flow-induced background or simply flow background, but it's really due to coupling between flow and non-flow. So in that sense, it is also non-flow here, but it's not the non-flow that I'm going to talk about here. It's not, they're related, but if you call this part non-flow, then this part of non-flow is taken care of. That's the main background. I'm talking about the additional non-flow contribution. So these measurements of the TPC are affected by non-flow. And as you can see, the non-flow in V2 is in the numerator because this is affected by non-flow V2. I should mention that I have the asterisk here for V2, meaning that this contains non-flow. If I don't have this asterisk, then that means real flow. So this is non-flow. This non-flow factor comes in, and this is C3 is due to three-particle intrinsic non-flow, and this is in the denominator. And as you can see, to some degree, they cancel each other. So that's a good thing to have. So you are not much affected by non-flow, but nevertheless, it's a quantitative question, how much is remaining. Never mind the algebra here. And now I'm back into Isobar because I'm talking about non-flow, and this is really the same non-flow. So in terms of Isobar, we do the ratio between ruthenium over zirconium. And again, 3-particle measurement, it's exactly the same thing, but we now have 2 systems, ruthenium and zirconium. And there we had only one system, gold-gold. So there we compare the 2 measurements in the same event, but with respect to PP and SP. So in SP, we don't have non-flow, only in PP. And here, Isobar, we are comparing 2 systems. So the idea is quite similar. You do 2 measurements, you get to the signal. But here you have non-flow in both systems. And you know, I have 3 pieces, basically. This piece, this pink magenta piece is canceled already up there because they're the same. This is the main flow-induced background, and the flow-induced background canceled in the FCME measurement, but they do not cancel in the Isobar measurements. And the blue one is the 3-particle non-flow, and the red one is the non-flow in the V2 measurement, and it's upside down. It's zirconium over ruthenium. And this is really a nasty problem. I'm still hopeful that we can get to it, but really that depends on the relative things of those terms. The baseline, the real baseline can be above or can be equal or below unity. I don't know. And I'm going to now speculate. My speculation is the following. We know that in delta-delta, non-flow in ruthenium is bigger. I actually expect, because ruthenium has higher energy density, the size is smaller, I expect that, you know, you can consider this to be jet, right? For instance, 2-particle correlation. I expect this term to be bigger in ruthenium than zirconium. And therefore, this is larger than 1. The blue term, I'm not certain. I certainly expect the 3-particle. So this is 3-particle correlation divided by 2-particle correlation. And I certainly expect this to be bigger in ruthenium than zirconium because the non-flow is just bigger in ruthenium. But it's divided by n V2 square, and n V2 square is a lot bigger in ruthenium than in zirconium. So it depends on the relative thing here. And my feeling is that since this is 3-particle correlation, you can get very nonlinear increase in 3-particle correlation. So this blue contribution could be positive, could be larger than 1, could be larger than unity. But it's possible that it's below unity. The red term, naively you would expect this should be smaller than 1 because ruthenium is downstairs. And it's not necessarily true, depending on how big the non-flow is, how big the non-flow difference is, because you already have difference in flow of 2 to 3%. If the non-flow in ruthenium is higher by more than 2 to 3%, then this thing will be smaller than 1 because ruthenium is downstairs here. If the non-flow difference is smaller than 2, if the non-flow difference is smaller than flow difference, then this term, red term, is actually bigger than 1. So my speculation or my guess, I wouldn't bet $1,000 on it, but my guess would be that the baseline is above unity. And now how far above unity is a quantitative question, and this really needs a very detailed, careful study, both experimentally and theoretically. So that's kind of my main conclusion here. I will skip these. For the FCME measurement in goal-to-goal collision, actually we did non-flow estimate, and turns out that the non-flow contribution is negative to FCME. And this is because actually with sub-events, with either gap, this 3-particle contribution takes over. So actually it's in the denominator, and therefore there is a negative non-flow contribution to FCME. So I'm now cautiously optimistic that there might be some indication, real indication of, well, should not say real indication, a hint, real hint of CME signal in the data, maybe on the order of 2 sigma effect. So this is what I have. I discussed. The real baseline is in terms of delta gamma over V2 is not unity. We should really multiply the multiplicity on it. And once we do that, the naive baseline is 1. I don't know why I have 98%. The naive baseline for kappa is 97%. And this depends, this is, I used the data already, used the delta difference already. And this is only naive expectation, and really how, quantitatively, what this baseline is really subject to non-flow difference between the 2 systems. Now, how well do we have to know this non-flow difference? Here I say that the non-flow, so I should say that the non-flow between delta is 3%, does not necessarily mean that the non-flow difference in other quantities must be 3%. It could be different. But if the non-flow difference between 2 systems is a couple of percent, say 2-3%, then we need to know this non-flow difference to a precision of 10%. That is 10% of that 3%. So we get to a precision of 0.003. The data precision is 0.004. So we might be hopeful to say something about CME signal quantitatively, or at least an upper limit of that. So I think it's right now open in my mind, and I think the signal, if there is a signal, the signal is very small, and it's probably just a couple of percent. A couple of sigma. But we have to do that. Before doing that, we don't really know. So that's my conclusion. We've achieved the 0.4% precision, and this is a big thanks to Starr, to Brookhaven, and to everyone involved, and everyone should be congratulated. I think the Isobar CME signal is very likely quite a bit smaller than that in goal-to-goal collisions. And the next step will be to understand the non-flow effects, and therefore the background baselines in the ratio. The goal-to-goal data may have some hint of positive CME signal. And I think we need more study and more data, and hopefully with 20 billion events goal-to-goal expected from 2023 and 25, we should be able to say something about more concretely something about the CME. If Mother Nature is kind, right, that there is a few percent signal in the data. I'm sorry for running over time. Somehow I thought that I would be able to finish within 1 hour. Thank you very much.
Okay, thank you. This is very, very helpful, and with such many details. So I think we open up to some questions. I see already some hands. Volker, please go ahead.
Yeah, so I want to go back to this whole non-flow story. I mean, I don't know. This is, for me, this is totally confusing. I measure delta, which is a well-defined two-particle correlation function. So I don't see why I have to talk about non-flow there. It's just two-particle correlations.
Yeah.
Now, hold on. Let me just finish, and then you can. And in gamma, I measure a three-particle correlation function, which is also well-defined. And then I do V2, and in V2, there are 10,000 different ways of doing it, and there I see the non-flow coming in. So why is in delta any non-flow? I mean, why nothing flows in delta? It's just a two-particle correlation function. So maybe it's just language, but I think it confuses the issue. So what's really the problem with delta?
I'm sorry, it's just language. It's delta is the little delta is two-particle correlation.
Correct.
Yeah, two-particle correlation. Yeah.
Yes.
Yeah,
but this changes from one system to the other, as does gamma. And unfortunately, the ratio comes out not at 1, but slightly below 1. So where is now, I don't see, I mean, I can see the multiplicity that I see, but that's the beauty of K, is that the multiplicity scaling is gone with this, right? And now the other problems, I can only see that the V2 difference plays into these K ratios. Is that where it really comes about?
Well, if you put, so the multiplicity ratio is really a trivial dilution effect that we should.
Right, but that doesn't affect K.
That does not affect K, yes.
Right.
The K is really the delta gamma over V2 divided by delta delta.
Right.
It is the additional delta delta that gives you an effect, because the delta delta are different between the two systems.
Well, sure. Why should that not be the case? The delta gamma is also different between the systems because both have depend on the multiplicity, and the hope is that in the ratio disappears. I mean, isn't that just the reason why one does this ratio?
Right. So the my take would be that, you know, the kappa does not offer something new. It's really in the delta gamma over V2 times n.
Fair enough. If I do it like that, that's possibly true. Although, I mean, I have to sit down and go back to our old work where we decomposed, as you, I mean, contrary what you said, I believe the signal in the delta from a possible CME is as big as in gamma, but that's another discussion, right? But I agree. I mean, delta gamma times n is probably a reasonable thing to do, right?
Yeah. So no, what you said is correct. That the CME signal in delta is as same as
in delta gamma.
In delta gamma. Yeah. It is the background that is a lot bigger in delta delta.
That's correct.
Yes. So therefore, but we are taking ratios here. So
yes.
So it's, you know, it's dominated by the background, factor of 10 bigger than that in delta gamma. So you know, you can pretty much neglect the CME contribution in delta delta.
Yes, that might be the case. Yes. Yeah. Well, obviously because it's 0, as we now learned, right?
Right.
Anyway, okay, thanks. I think I know where you're coming from here. Okay. Thank you.
Yeah. But the delta delta is important to measure because that gives you a feeling about the difference in those angular correlations between the two systems, and that you kind of you know rough estimate for other non-flow contributions between the two systems.
Okay, thank you.
Okay, no.
Yeah, hi, Fuqiang. Thank you for the talk.
I know.
I have a simple question now. If we can turn time back, let's say turn back 5 years, what would you do differently in terms of isobar collision? What will, if we have 5 more years and we still have an opportunity to run isobar collisions, what would you do differently?
If we, I don't know, if we knew that that the V2s will be different. And we knew that those non-flows would be different. And we knew that the signal could be a lot smaller. I simply will not do it. It's actually better to accumulate goal-to-goal statistics, or actually running goal-to-goal at a lower energy, for instance, and that of course requires theoretical input where in energy you expect a larger CME signal, because this is critically depending on the lifetime of the magnetic field. So that's a good question, and if we knew that, then I wouldn't run Isobar, but you never know, right? That if the signal, the Glasma estimate by Jingfen and the company in terms of the initial axial charge density, they found that actually the Isobar axial charge density is bigger than gold-to-gold. And therefore, you can expect a bigger signal in Isobar than gold-to-gold, relatively speaking. Yeah, but my feeling is that given the Isobar data, and we don't see a signal, and I have to be honest, my feeling is that after we know the baseline precisely, and assume the baseline is above 1, it will be probably a cup of sigma effect. So my feeling is that based on that, it really seems to be true that the signal in Isobar is smaller than in gold-to-gold. Because if they're the same, then you would expect 3 sigma.
Thank you.
Can I add to this as a member of the PAC and the committee who proposed or supported the Isobar run? When I saw these results yesterday on Tuesday, I thought maybe we did something wrong, because Fuqiang, you had papers out there a while back predicting that there is this difference because of this EFT calculation, right?
Right.
And so maybe we should have asked STAR to release the V2 and the multiplicities while still keeping the CME results blind. I'm not sure if this can be done in practice, right? So that actually the theorists and everybody out there based on this could actually make a pre-release baseline, because now it's going to be all murky, unfortunately, because now we realize the baseline is likely different, right? So that's what I'm really regretting, that we didn't think about this. So that if everybody would have agreed the baseline is at whatever 0.97, whatever it comes out, right? I mean, after doing all this, what you call non-flow analysis, and then the data would have been unblinded, maybe it would be much more credible, right? I mean, now it's unfortunate that we have to sort of backpedal, right?
Well,
but what can I say?
Well, but yes and no, right? That I think this is a blind analysis, and that's what we have, and now
Yes.
we're since it's unblinded, now we can do whatever we want, right? Now we
but
improve our understanding. So I don't think that
it will be much harder sell out to the outside community now that the bag is out of the cat is out of the bag, right? So that's really unfortunate for all this effort here. Anyway.
Yeah, that's probably true, but yeah, it's but I think it's okay. Since we understand it, I mean I mean the multiplicity scaling is really a simple thing, and everyone knows. It's just that it's an overlook on our part. It's fortunate, but I don't regret much, because that's the data is here. We know the multiplicities. We don't have to we concluded in our paper. We said that with the predefined criteria, we don't see it.
Right.
and we know exactly what it is. So I think.
But Fuqiang, by the way, I mean your slides here. So even if I'm just said you want to do naive multiplicity scaling, it's like smaller than 3%, but the data is still below that, right?
No. Here is on the screen, right? Once you do the multiplicity scaling, this would be your baseline, right? This is your baseline because
you said 3%. Its baseline is less than 3%, but that's 4% now.
The 3% is for the kappa. Is for kappa. So for the green points, for the points in green,
I see.
The baseline would be 7%. This is the line that I draw here, the green line.
Okay.
Yeah.
So this is why Qingfen claimed that if you do the naive scaling, the data point is above. The multiplicity scales baseline.
Yes. So with the naive scaling, all the data points are actually above right now. And the real question is really what the real scaling, what the real baseline is.
Okay. I see another question from Precious.
I just wanted to say that if you look at this plot, add a comment on what Fuqiang was saying. This is for 20 to 50%. So if you really want to compare with multiplicity baseline, the best thing would be do it in every centrality bin. Fuqiang, you had a slide, right, where you inverted the multiplicity plot.
Yeah.
So right here, right?
This one, yeah.
So it's better to compare the multiplicities in each bin with the delta gamma over V2.
Right.
Then you can probably multiply and then average. It's not a good idea to first average over a big centrality 20 to 50%, and then that, because this brings uncertainty.
Right. Yes.
Then maybe you can see that they how far they are. And this we didn't have in our blinding procedure.
Yes. This one easily. Yes.
Yeah, that's one comment. And just another quick comment is multiplicity is also an uncorrected quantity. So we hope that the efficiency and other corrections are small. I mean, it doesn't probably matter, but it's not as good as delta gamma over V2, which are all ratio observable. So cosine, they cancel some efficiency, but multiplicity is not immune to those detector uncertainty effects and other effects.
Right.
So you have to be careful when you multiply and conclude.
Right. Yeah. So this is really the first step. Yeah. That, and I assume, I hope that the next paper from Star on Isobar will take care of all those.
Yeah. Are you finished? Are you done?
Sorry, I just need to lower my hand.
Kafi.
Yes, very nice talk. I just have a very, very naive question. If this thing, the CME is from the topological term, the theta term in QCD, wouldn't you expect that the effects that you see will be of the order of theta, like the neutron electric dipole moment? There'll be many order of magnitude than the whatever you call the FCME. It's just order of magnitude. I don't quite understand why it can be so big.
That I don't know, but I assume that in our heavy ion collisions, we have deconfinement, we have high temperature, and we have this vacuum where the theta is not zero.
Yes, theta is not zero, but we know it's very, very small.
Right. No, but what I mean is not 0, 0. It's 1 or something like that.
It's 1. Why is it 1?
Oh, well, if
it's a parameter. it's a
well, if you don't have this if you don't have this topological gluon field, then of course there will be no such physics. So I assume that I don't know. So that's my understanding that you
either in high temperature or low temperature and so on. Well, when, for example, if you calculate neutron electric dipole moment,
yes,
you put that in the theta vacuum, the different topological sector, whatever. But because the theta is so small, it's in action, so it's e to the I theta times the topological charge, right? Now, so it's so small, you expand it. So whatever observable you want to look at, it's either the delta gamma or whatever it is, it will multiply by the theta times the topological charge. Right? So there's a correlation between the topological charge, which is an active parity CP and whatever observable in the current in parallel to the electromagnetic B fields. That will be a parity negative, so that it can come to a thing. But that is everything's proportional to theta.
Yeah, but so as I said that, so I thought the idea was that this theta is not so. When the temperature was very high, this theta is an angle that is on the order of 1. And then when the temperature cools down to 0 degree, then this theta comes to 0. So nowadays at our universe, the theta is 0, and that's shown by the EDM measurement. That you have upper limit of ridiculously 10 to the minus 26, something like that. Yeah, I don't know. I'm not an expert at all, of course. So if the theta is 0, then I thought then there would be no CME, right?
Sure.
Because that term is not there.
That's true.
But the idea was that the theta is not 0 at high temperature, and therefore you can have different vacuum states with different topological charges, and fluctuations, and then you have transitions between different states, so you could have the chiral anomaly.
That big. All right. Yeah. Thank you. I'll have to think about it.
Okay. I think we really now run out of time, and but what the discussion and talk is very exciting. And I want to thank Fuqiang again.
Thank you.
Okay. Thank you.